All right, folks, in this lesson, what we're going to do is we're going to look at a couple numerical examples where we are comparing free energy, delta G, to our equilibrium constant K. And we're going to look at how we can relate our equilibrium constant to the spontaneity of a reaction. So in this first example, what we want to do is we want to calculate the equilibrium constant K sub P. And we're given this reaction, 2H2O dissociates to form 2H2 plus O2. And we're given delta G of formation. So the first thing you always want to do is you want to look at the reaction and you want to come up with some sort of expectation. Sometimes you'll see a reaction where you have no idea what's going on, but here is an example of a reaction where you should have some sort of idea whether this reaction is spontaneous or not. So for instance, this reaction, in the reactants we have H2O, and then in the products, H2O is broken down into H2 and O2. So how often do we see water decompose into hydrogen and oxygen gas spontaneously? We don't see it. So this should indicate to you right away that as we're going through and solving for a delta G before we find the equilibrium constant, that delta G should indicate that it's a non-spontaneous process. So the expectation from the get-go is that delta G is equal to some positive value. So recall that we can find delta G of the reaction from delta G of formation. So we can go ahead and do that. So in this particular problem, we're given the information for delta G of formation of water. And we aren't given delta G of formation of hydrogen or oxygen. And the reason why is because these exist in their standard state. And we know that delta G of formation is 0. So we could write out products minus reactants. Here's our products, 2 moles of hydrogen at 0 kilojoules per mole plus 1 mole of oxygen at 0 kilojoules per mole. That's the products part. Minus our reactants, so we have 2 moles of H2O times delta G of formation, which is 237.2 kilojoules per mole. So whenever we plug this in, we'll get delta G of reaction to be negative 474.4 kilojoules. So this indicates that this is a non-spontaneous process, just as we predicted. So now, if we want to find the equilibrium constant K, we have an equation that relates delta G to K. So we have delta G is equal to negative RT ln of K. And so now we can substitute in. But before we substitute in, let's go ahead and rearrange this and solve for K. So we'll have to divide both sides by negative RT. Okay, so negative RT cancels out over here. Then to get rid of the natural log, I have to take the natural exponential of that. So we have K is equal to E to the negative delta G over RT. So whenever we plug in here, we're going to have E to the negative 474.4 kilojoules. And typically whenever we're plugging into equation, we relate this to kilojoules per mole because we're looking at a reaction. But you just have to really watch your units as you're going through, because sometimes delta G is expressed in terms of kilojoules per mole for kind of how many iterations it's going through a reaction. Other times it's just given as a total value of kilojoules. And this is divided by RT. So R in this case needs to be converted to kilojoules. So we have 0.008314 kilojoules per mole Kelvin times our temperature, which is 298 K. So whenever you plug all this in, you will end up getting your equilibrium constant K is equal to 6.95 times 10 to the negative 84th. And so this indicates to you, if you were to write out your expression for K, K is equal to the pressure of H2 squared times the pressure of O2. And then we aren't going to include the pressure of water because it's a liquid. So because the value of K is so small, it's to the negative 84th power, What this indicates to you is this reaction is primarily reactants. There's minimal products present, so it's primarily H2O. So let's go ahead and look at another example. In this example, what we're going to do is we are going to calculate the free energy for the solubility product of silver chloride. And then we're going to figure out which side does the equilibrium favor. We probably already have an idea based off of the KSP value having an order of magnitude that's to -10th. So if we look at this, let's go ahead and start by writing our reaction. So we have AgCl, so silver chloride. And its solubility product would be silver ion plus the chloride ion. And so now, if we want to solve for delta G, we know that delta G is equal to negative RT ln of K. We can plug in for R, so we have 8.314 joules per mole Kelvin. We have our temperature, which is 298 K. And then we have K, which was given to us in the problem, so the natural log of 1.6 times 10 to the -10th. Whenever we plug this in, we'll get delta G for this reaction, the solubility product, to be 55.9 kilojoules per mole. All right, so if we look at delta G, we can see that it's a positive value. So delta G is greater than 0, which means this is a non-spontaneous process. So if it's a non-spontaneous process, it means the reaction is going to favor the reactants. It's not going to spontaneously go on to form products. All right, so this is it. So we are done with thermodynamics now.